Hello and welcome to Lecture 2 of the Oscillations unit of PHYS 1201, and this lecture is going to be all about simple harmonic oscillations. And there's a lot to know about simple harmonic oscillations, so we will not be done at the end of this lecture. But the main point of this lecture is that we're going to see the two quite different defining features of simple harmonic oscillations. Let's talk about the simplest case of a simple harmonic oscillator. If it's a vertical oscillator, then we have to worry about a spring force and a weight. Now that actually doesn't make things any more complicated, but it takes a little bit of effort to show that it doesn't make things any more complicated. So let's start out with this horizontal case. So we have a mass, it's on a frictionless surface, so maybe it's an air puck or a glider on an air track or something like that, and it's attached to a spring. And it's sitting here at the equilibrium length of the spring. This is what makes the horizontal case easier. When you haven't pulled on the mass at all, it will sit at the equilibrium length of the spring. And let's just recall from last semester what we mean by that. This is the length that the spring is when no force is exerted on it. And by Newton's third law, that means that when it's at this length, the spring exerts no force. Now, at any other length, the spring always pulls or pushes, as the case may be, back towards the equilibrium. So if we push the block a little bit this way, compressing the spring, then the force that the spring exerts on the mass is back opposite the direction we pushed the mass towards the equilibrium position. And no matter where we push the block, that force always points back towards the equilibrium position. And if we pull or push it farther from the equilibrium position, that force gets bigger. This is something we know about springs. So notice that this is a case where the force always points back towards the equilibrium position, and that means this is always a restoring force. And so this meets the condition that we expect for oscillations to happen, the presence of a restoring force. The restoring force that we get when we have a spring as the thing that supplies the force is special. Remember that for a spring force, the force is proportional to the displacement from equilibrium. So here's our relation. I've put vector symbols on to indicate that we're talking about direction. And remember that this delta x here is the displacement of the end of the spring from its equilibrium position. K is the stiffness of the spring, and this negative is just saying that whichever way the displacement from equilibrium is, the force exerted by the spring is opposite that, just like I've drawn here. Now, for our purposes, thinking about harmonic oscillators, it's always going to be convenient to set our origin, our axes, at the equilibrium position. And that leads to a nice little simplification, because with the axes there, now the displacement from equilibrium is just the same thing as the position. So instead of delta x, we can just write x. And furthermore, most of the time we're going to be restricting our attention to one-dimensional cases, and so much of the time we don't even care about these vector symbols because we're in one dimension and just saying, say, right is positive and left is negative, or up and down, whichever the case may be, is all we need to do to keep track of all the direction information that we ever need. So a lot of the time we can just drop the vector symbols even. But the thing that's even more special is the form of the force due to a spring. It's a linear function of the position. Now, generally, when you have an oscillation, this isn't always the case, but for a mass on a spring it is, and it's going to turn out to lead to special behavior. So we tend to look out for this and say that this idea of a linear restoring force is the identifying feature of simple harmonic oscillations. Because if a mass on a spring acts this way because of this restoring force, any other system you come across that happens to also have a linear restoring force, you know that it's going to oscillate exactly the same as a mass on a spring. And so this is why this idea of simple harmonic oscillation is useful as sort of a category of motion, because it's not just masses on springs that do it. For example, pretty much all elastic forces are linear, and so things like vibrating strings and bending structures like buildings swaying in the wind end up having linear restoring forces, and so they execute oscillations that are just like a mass on a spring. But there are some other surprising examples. A pendulum, as long as it does small oscillations, as we'll see, turns out to have a linear restoring force, and so it also oscillates the same way as a mass on a spring does. And that's sort of surprising, the idea that a pendulum ends up carrying out the same sorts of oscillations as a mass on a spring is sort of surprising if you think about it, because they're very different systems. It turns out that there's a close relationship between simple harmonic oscillations and uniform circular motion, and this relationship is going to be useful to us. So you can show this relationship through an experiment. Now, it's difficult to actually do this in practice, so I haven't been able to do it, but underneath this video I'll post some links to other videos on YouTube where other people do this experiment, and you'll see in some of them that they have some trouble doing it. But here's how it works. You have a mass on a spring. So this is our simple harmonic oscillator. And you have an object on, say, a turntable or some other way of making something go in a circle. And you arrange it so that the period of this thing going around the circle is the same as the period of your simple harmonic oscillator. So that's one of the difficulties of the experiment. That takes some arranging. You also need to match the amplitude of the oscillation to the radius of the circle, and what's more, you need to get the equilibrium position of your oscillation lined up with the middle of the circle. And then you shine a light, and you're going to look at the shadows. And you set it up so that at the moment you release your mass, the shadows are on top of each other. And what you find then, as you watch it, is that the shadows stay exactly in sync with each other. They go around the circle in lockstep. Now, if you think about that, that's sort of surprising. These are very different motions. This thing is going in a circle. This is a mass on a spring. These are seemingly unconnected, and yet they move in lockstep. So this is a very useful little observation, and we're going to use it in a moment to develop some expressions that are going to be very useful for us analyzing simple harmonic oscillations. Let's look at what this close relationship between uniform circular motion and simple harmonic oscillations can tell us. Let's say we've done this setup. So we've got our circular motion with some radius and its uniform speed, and we've got our harmonic oscillation going on down here, and we've lined them up so that the equilibrium position of the mass is right here where I've put the axes, and that is lined up underneath the center of the circle. And let's say we've arranged for the amplitude of this to be the same as this radius, and for the periods to be synchronized. So let's just note that down. We have a period of the oscillator is the same as the period of the thing going in the circle, and we'll just call those both capital T. And we have the radius of the circle is the same as the amplitude of the oscillation. And now notice that this distance here, that is the x position of the thing going in the circle. But it's also the same distance as the x position of the oscillator. So the other thing we have is that x for the oscillator is the same as, this is really the x component of the position vector of the thing going in a circle. And these things are going to be the key for us being able to write down what the position of the oscillator is as a function of time. That's our goal here. So let's see. We have some angle theta, okay? As this goes around, there's always some angle theta, and this is changing with time. And at any given time, we know that xc is just, if you just look here, there's a triangle, there's a right angle there, the hypotenuse is r, there's the angle theta, there's the x, and so xc is just r cos theta. And so if we just knew how theta varied with time, then we would have this as a function of time. But that's easy because this is uniform circular motion. So this thing is going equal distances around the edge of the circle in equal times, which means this angle is increasing at a constant rate. And we know what that looks like as a graph. Whenever you have something increasing at a constant rate, that means you have a linear graph. And so our theta versus time graph must just be a straight line, and we can define things so that at t equals 0, theta is 0. We're just saying that t equals 0 is when this passes through this point. And now look what that tells us. In a time equal to the period, this goes around a full circle. Now, it's tempting to write 360 degrees here, but it's actually more convenient to work in radians. And hopefully you know that a full circle is 2 pi radians. And so what we have now is a line where we can see that theta is the slope of this line times t. And that slope is just a rise over a run, and that rise is 2 pi, and that run is capital T, and so there we have it. Theta just goes like this. And so that is our xc. It is r cosine 2 pi over the period times t. And we know that that's the same as xo. But for xo, we don't want to write r. We want to write this all in terms of properties of that motion. But we know that the radius is the same as the amplitude. And so there is our final relationship, and we'll use this over and over again. This gives us, at any time now, we can say what the position is of the oscillator. So I'll just finish off this lecture by pointing out that we now have 2 different definitions of simple harmonic oscillation, or ways of recognizing it. The first is if there's a linear restoring force, then we know this is something that is like a mass on a spring, and so it will execute simple harmonic oscillations. But the other is if you see sinusoidal motion. Okay, so if your data looks like this, then you know that's simple harmonic oscillations as well. And the presence of either of these, a linear restoring force or sinusoidal motion, means that what you are dealing with is simple harmonic oscillations. You can take either one of these as a definition of it. And you can show, we haven't really shown, you need some calculus to do it. You can show that the one implies the other. If you see a system and you analyze it and find that it has a linear restoring force, then you can bet your boots that when you look at its position versus time, it's going to be sinusoidal. And likewise, when you see sinusoidal motion, you can bet that the culprit responsible for that sinusoidal motion is a linear restoring force.